What if I told you that a simple circuit with no external power source could show us the pure natural flow of energy as it creates an elegant exponential decay? Welcome to the fascinating world of the source-free RC circuits. Simple yet fundamental. It is the cornerstone of understanding how energy behaves in electronics. From safely discharging capacitors in high voltage systems to analyzing power down behaviors in electronics, the applications are everywhere. And it all comes down to one critical parameter, the time constant tau. In this video, we'll dive into the natural response of the source-free RC circuits, explore the math behind exponential decay, and see why this concept is essential in electronics. To begin, we charge the capacitor by closing the switch. Let the voltage across the capacitor at any time t be given as V of t. Once the capacitor is fully charged, we set t is equal to 0 as the initial reference point. Given that the capacitor starts fully charged, we can assume the initial voltage across it at t is equal to 0 as V0. Applying the KCL at this particular node, we get the following equation. The current through the capacitor is given by C dV by dt, and the current through the resistor can be written as V upon R. Upon simplification, we get the first order differential equation. To solve it, we rearrange the terms. Now we integrate both sides of this equation. Here, ln of a is the integration constant. Now, taking the power of e on both sides, we get the final equation. That is v of t is equal to a e power minus t by rc. But from the initial conditions, we know that voltage at time t is equal to 0 is nothing but V0. Hence, we can write the final equation as V0 e power minus t by RC. So this shows us that the voltage response of the RC circuit is an exponential decay of the initial charged voltage. And since the response is actually due to the initial energy stored and the physical characteristics of the circuit and not due to some external voltage or a current source, this is called the natural response of the circuit. Let us now look more closely at the natural response. So here we see that at t is equal to 0, we have the voltage stored in the capacitor as V0. And as t increases, the voltage decreases towards 0. Now, the rate at which the voltage decreases is expressed in terms of time constant, denoted by tau. So the time constant of a circuit is the time required for the response to decay to a factor of 1 upon e, or 36.8% of its initial value. So at t is equal to tau, we get the following equation. Let us look more closely at the normalized natural response in terms of time constants. So here we see that the voltage V of t is less than 1% of its initial value, that is V0 after 5 time constants. So after 5 time constants, capacitor is typically considered fully discharged, as the circuit reaches its steady state with no further changes. During each time interval of 1 time constant, the voltage drops by 36.8% of its current value, no matter when the interval occurs. Now let us explore this concept in greater detail. We have 4 circuits, each with a different time constant. In this scenario, all the capacitors are fully charged. To analyze the behavior, we pause the simulation and open all the switches simultaneously. This ensures that when we rerun the simulation, all the capacitors will begin discharging at the same time. The discharge time varies depending on the time constant of each circuit. As the time constant is determined by the resistance and the capacitance, we can calculate the time constant for each circuit. Circuit 1 has a time constant of 1 millisecond. Circuit 2 has a time constant of 2 milliseconds. Circuit 3 and 4 have time constants of 0.5 and 3 milliseconds. We can verify this using the graph above. Since all the capacitors were initially charged to 1 volt, the time constant can be determined as the time it takes for the voltage to drop to approximately 36.8% of its initial value. The time constant tau controls how quickly an RC circuit responds. A smaller tau means the voltage drops faster, leading to a quick steady state due to rapid energy dissipation. In contrast, a larger tau causes a slower response, taking longer to reach the steady state. Regardless of whether tau is small or large, the circuit reaches its steady state within 5 time constants.